welcome to our final NLP talk for the week. We saved the best to last, of course. So we're delighted to have Ekaterina or Katya Kochmar visiting us. Katya is a lecturer at the University of Bath in part of the AI group. She's prior to starting at the University of Bath, she was a postdoc, part of that, a PhD student at Cambridge University, and part of the ALTER, the Automated Language Assessment, Teaching and Assessment Institute. My apologies. She's also a co-founder and chief scientific officer of Korbit AI, and which relates to dialogue systems for language teaching purposes. Also, that's very cool. And today she's talking to us about automated generation of personalized pedagogical interventions in ITS.
Thank you very much. Very glad to be here, and today I'm going to tell you a bit about automated generation of personalized pedagogical interventions into intelligent tutoring systems, ITS for short. So Tim already introduced this idea a bit. So this talk is going to combine the natural language processing related components with machine learning oriented methods, and also I will tell a bit more about the approaches to educational applications that I'm working on and I have been working on during my PhD as well. So first of all, I think the majority of us here are related to the educational domain in some ways. So either we are, for example, lecturers, or we are students. And I suppose we all would agree that we as students differ as when we come at a different subjects, at new subjects, we differ in terms of our abilities, in terms of our interests, in terms of the backgrounds with which we approach new subjects. And this is a big challenge. For the lecturers and for the teachers, this is obviously a big challenge as well. And it has been shown that personalization, therefore, is one of the key, most successful sort of core ideas in the education. This is very important for successful learning, and therefore we can also define it as one size doesn't fit all. Have we seen any proof of that? Sort of on top of just some anecdotal evidence, we all know that we would like to have some personalized learning. Yes, we did. In 1984, Benjamin Bloom, an educational psychologist, ran a study where he basically split students in two groups. One of them was a control group who received the learning in the traditional conventional way, where the learning was delivered in a classroom in a big sort of group of people. And as a comparison to that, a second group of students received personalized one-on-one tutoring. As a result of that, when the tests were run, at the end of this learning period, it turns out that an average student from the group of students who received this personalized one-on-one tutoring were able to perform better than an average student from the control group with the effect sizes large as 2 standard deviations. This basically translates into an average student from this personalized group performing better than 98% of the students in the control group. So this is quite a huge improvement, but of course, if you think about that, personalized tutoring is not available to everyone. It's very expensive to implement that, and in many societies, we can't even talk about personalized tutoring. Even high quality education itself is quite challenging to provide people with. So this is precisely where such systems like intelligent tutoring systems and the technology, AI-driven approaches can help us to bridge this gap. And this is precisely what I'm going to talk about today. So in general, intelligent tutoring systems are defined as computer-based instructional systems with models of instructional contents that specify what to teach, and the strategies, teaching strategies that specify how to teach. So essentially, if we think about that, this is a viable alternative to human teachers, but I'm not going to say that it is a replacement for human teachers. The idea here is that certain aspects of the learning that should be personalized can be approached using the ITS, and so I will show some examples of how this can be done in practice. And ideally, therefore, we can develop a system, we can imagine a system in which the human tutors will be complemented with such ITS intelligent tutoring systems to address the gaps in the traditional education where human tutors cannot possibly address these personalized sort of issues with the students and provide them with high quality education. And for example, pandemic presented a very good illustration for why this is challenging, because during the pandemic, we all moved to the online education not by choice, but by necessity, and we all, I think, understood the challenges there. So this is precisely where such systems can actually help us to provide, so either to get a better education or to provide people with better education. So the Korbit Intelligent Tutoring System is, I'm going to use it as an example, and as Tim mentioned, I co-founded a company that builds such an intelligent tutoring system. Specifically, it is a large-scale AI-powered intelligent tutoring system, which is delivering the learning through a dialogue. We will see an example in a couple of slides. So I say that it is AI-powered because lots of the components in this system are basically run by natural language processing models and by machine learning models. Specifically, the personalization there is ensured by the use of such techniques. So the system itself, first of all, we spent a couple of years developing the very first prototype, and it was launched as an intelligent tutoring system, which is accessible to anyone all over the world for free since 2019, and we have a user base or learner base of over 20,000 students that are enrolled in the courses. Specifically, at the moment, we are addressing STEM subjects. So that means we are teaching students about, for example, machine learning and AI using an AI-driven intelligent tutoring system. So on the right here, you can see the AI tutor called Korbit, and here is what happens when the student signs up to go through a course to learn about a particular subject. So first of all, just like in a classroom, the material is presented to the students by video lectures. So we prepared some lectures that cover the material, and this sort of mimics how we would normally learn about the subject in a classroom. So we also recognize that students have different learning styles, so we all learn by different means. Some of us learn better through visual aids, others through auditory means. Some of us prefer reading and writing, and kinesthetic way of learning is when we learn through doing something. So we believe that with the video lectures, we already cover some of these different modalities, but with further interactions, of which you'll see some examples, we are also able to cover the other modalities among those four that are usually distinguished between. So once the student has seen a video lecture that presents the material, the AI tutor follows or engages the students in a dialogue. So first of all, she would ask some questions about the material that was presented in the lecture. For example, here, she would ask the students about the methods or the ways the machine learning models learn or train. And as an answer, it would expect the students to say something about the training data. Then the answer, so this is a short demo and it goes in a loop, so you would see this example again. Essentially, after the student provides an answer, it's a bit like a chatbot. The answer is evaluated in the background using a suite of natural language processing techniques and methods and machine learning models. And then depending on the outcome of this, so if the answer is correct, then the AI tutor would complement the student on that and would move to the next question. If the answer is correct, then the AI tutor will follow up with some further interactions that would nudge the students in the right direction to actually address the misunderstandings that the student has. And this is where it becomes personalized for each particular student. So as you can see, some of these follow-up interactions, some of them would be the free-form questions and answers. Others would be more typical for the computer-based environments, like, for example, this multiple-choice question here. So to summarize, we provide video lectures that present the core material about the subject. And after that, the answers provided by the students are evaluated using NLP and machine learning models. And after that, the student receives personalized feedback. So, for example, if two different students started learning about the subject, quite quickly, their particular learning journeys will deviate from each other. because this interaction, this dialogue there, will be personalized for each particular, or will be adapted to each particular student. So as I already mentioned, speaking about the range of different exercises, the majority of them will be these free-form exercises. So these will be questions followed by answers, and therefore it will be a dialogue that is similar to what you would have in in-person teaching, or if you wish, as you have seen, this looks a bit like a messaging app. But also, in addition to that, we cover these more traditional types of exercises that you would find, for example, in a range of MOOCs, like the massive online open courses. This includes the multiple choice questions, on the gap exercises, concept rebuilding exercises, and so on. So we are diversifying the interactions of the platforms, and essentially we also have models that select which of these types of exercises would be the most successful in each particular situation during the dialogue with the students. On top of that, due to the nature of the subjects that we are addressing, these STEM subjects, quite a lot of it is naturally expressed not just in natural language, but also in terms of mathematical definitions and coding exercises. So a particular challenge here, which we are working on right now, it's still an ongoing research, is how to translate between the ideas that are expressed in natural language and the ideas that are presented in terms of mathematical definitions and, for example, in programming languages. I'm not going to talk much about that, just to sort of present you with the further ideas that are parts of this system here and the research challenges that we have. So essentially, I'm going to summarize what are the key components that we have in this system and how we approach learning on this system. The first component, as I mentioned, is very important to provide students with personalized learning. And personalized learning here starts from the very beginning, where we are, when the student signs up on the platform, we are assessing their knowledge by understanding what would be the knowledge gaps sort of related to our material and how to structure the lessons, how to structure the modules, and in what order they should be provided for the students. So once again, there is room for improvement here because there are lots of approaches that can be applied here to personalize this even further. So once the students start engaging in the dialogue, then as you have seen, we have different types of exercises and different types of feedback that we can provide. All of these can and should be personalized for the specific needs of each particular student. And this is where we are using the NLP and machine learning techniques. This is the first aspect that is very important to provide in education in general and in distance-based learning in particular, because obviously we know that, for example, when we are all in one classroom, this is a bit more engaging, a bit more personalized if we have questions that can be addressed on a personalized basis. When we move to distance-based learning, this all might become quite boring and quite tedious if we don't have these components involved. But one other component that is also very important is interactivity. And this is one of the major problems, for example, with the MOOC courses. As you might know, lots of people are interested in starting them, but the dropout rate on those courses is quite high, partly due to the fact that there is essentially no interactivity in such learning. So it is a very passive mode of learning where you watch a video lecture and there is no follow-up on that. In contrast, what we do here, we're using the Socratic tutoring methods as the basis for what we are doing. So essentially, we're engaging the students in the active dialogue all the time. We're talking to them by the means of the AI tutor. And here, the questions are leading the students and ideally providing them with the right line of reasoning about this material. So how do we know that this works? Again, there is a lot of research in educational psychology that proves and shows that these ideas and these methods are very effective. I'm citing only two, some of the most popular papers here, but essentially the way we structure that is a dialogue where the conversation is driven by the AI tutor, by the questions that the AI tutor poses for the students, and this has been shown as an effective way of learning. But once the student answers the question, remember that sometimes they also may answer these questions incorrectly. What should we do in such a case? There are different ways. One of them would be to just provide students with the correct answer. Say, you are incorrect, here is what's it should be. But the research shows that this is not a successful way of learning, and a much better way would be to provide students with either follow-up questions or so-called hints, where we are bit by bit directing them in the right along the right lines for the reasoning about the question. I mentioned the zone of proximal development here. This idea relates to the fact that if we challenge the students at a too low level, so we ask them something about what they already know, this will be too trivial, and essentially in the context of the intelligent tutoring systems, this will quickly become very boring. If we challenge them too much, asking them questions that they cannot answer, this will become very challenging to the point of frustration. So therefore, it's quite important to identify what would be the right level of providing the hints and providing the exercises. This is something that can be integrated into these models as well. And finally, the last sort of key bit to what we're doing is the idea of active learning. And in this case, active learning is not the machine learning term of active learning, but rather the idea in the learning sciences of how we learn to do things. So this is learning by doing. When we challenge the students at all levels, for example, with the problem-solving exercises that are expressed in natural language, with the mathematical questions where they need to solve something, and also with the coding exercises in real-life projects, we're asking them to apply their knowledge and their skills to actual tasks and actual problems. And there is a widely known bias, cognitive bias. This reference here would tell you about the research by the researchers from CMU, where they discuss this bias. Essentially, the learning bias tells us, or the illusion of learning bias tells us that until students are challenged, are asked to implement the skills, or until we are asked, any one of us, it's very hard for us to understand whether we actually truly know something or not. Having read something about the subject, say some learning material, having gone through the learning material, having gone through the lecture, we might have an idea that we now mastered this subject. But until we try to apply this knowledge, it is actually very hard to evaluate whether we do or do not know something. Where are our knowledge gaps? I will tell you more about this in the course of the presentation as well, but for now, I'm just putting it out there. So to summarize what we do with this intelligent tutoring system, and what is at the core of it is personalized learning, where we're trying at every step to adapt this to the particular learning journey for each student. Interactive learning, where the learning is organized in the form of natural dialogue. And finally, active learning, where the students are challenged to do things all the time. And now at this point, I'll tell you a bit more about how we actually generate such personalized feedback in practice using natural language processing techniques. So essentially, as I said, we have a wide range of different types of pedagogical interventions. We have about a dozen of them, and they include, among others, textual hints, concept trees, multiple choice quizzes, and so on. So at the core, we have the machine learning models. For instance, one of them uses the reinforcement learning techniques to identify for each particular student at each step of the dialogue what would be the most successful type of the intervention to provide the students with. And then, for instance, say it selects the text hint in this particular case. So the question that is presented here, what is a linear regression model, describe it in one sentence, and the student provides some answer. That is roughly along the right lines, but we would like to learn more about this topic from the student, or to extract more from the student. So then, if the model selected that a textual hint should be provided, the question is which particular hint we should be selecting. So that's where we are basically involving the personalized selection of such hints. Where do the hints come from in the first place? Originally, we have created a range of different hints manually at the very beginning when we just started working on this system and collecting the data. But of course, whatever way we structure the hints, this wouldn't be able to cover all possible types of misunderstandings and all possible types of further suggestions that we can provide. And here is where we can use the natural language processing techniques. This is a very simple system that I'm going to show you examples of. Essentially, suppose we have some questions that are asked from the students. For instance, what is the difference between overfitting and underfitting? Or would you use linear regression or logistic regression to model a classification problem? So the very first step here is to identify what the question asks about by extracting the key concepts that are present in such a question. In the first case, this would include difference that the student is asked to define, and overfitting and underfitting. In the second case, such key concepts would include logistic regression, linear regression, and classification problem. So this can be done using natural language processing approaches and extracting the key phrases from the question itself. Then what we have at the core of the system is a range of different solutions, the reference solutions or expectations, as we call them here. Again, this is a limited set, and this is just the starting point, because using the natural language processing techniques, we can also further increase and expand the set of such solutions. But suppose we have as at the background the solutions or the expectations, which are phrased as following. For the first question, for instance, we have a solution, a model is underfitting when it has a high bias. And for the second one, we have a solution that says I would use logistic regression because the outputs are discrete. So how can we provide the hints based on this reference solution? Suppose we are seeking to receive such a solution from a student. Of course, if we just reveal the solution or reveal the part that contains the keywords, this will actually be trivial for the student to solve. And this relates back to the idea that we would like to direct the students in the right direction by providing them with some ideas that will help them to arrive at the correct solution, but without revealing them the key bits of the solution. So now using parsing, we are able to split these sentences into the constituent parts or the clauses. In the first case, this would be a model is underfitting one bit, and when it has high bias, another bit. In the second example, this will be I would use logistic regression, one part, and because the outputs are discrete as the second part. So now what we don't want to reveal is the part of the sentence that contains the key concepts from this exercise. What we can do, though, is generate further hints containing the ideas from the parts of the reference solution that do not contain the keywords and key phrases, which are used here. So, for example, we would suggest that the student thinks about the cases where the model has a high bias, or when the outputs are discrete for the second case. And in that case, the student would start thinking about the related concepts that would lead them to the correct answer without actually getting the correct answer in the first place. Now, when we have the range of these different hints, what we do, we also select them for each particular student in the at every particular step in the dialogue, using the machine learning models that rely on the features extracted from these hints and evaluate the quality of the hints from the linguistic point of view. For example, how well formed such a sentence is, as well as the personal performance metrics that are related to each student. For example, how many exercises have they solved successfully? How long is the dialogue that they had with the AI tutor before, and so on. So based on all of these different features, we can select between these hints to provide students with more personalized hints. But still, this is a very simple model that doesn't address many of the issues and the problems that the students may have. So as the follow-up research idea here, we decided to dig deeper into the questions and the hints themselves. And the specific aspect that we explored here is the following. So many of the questions that we have would ask students to provide the answer, as well as an elaboration or the reasoning for this answer. This is just one type of the structure for the questions. There may be others. But suppose in this case, the student is asked whether, when they're given a data set of the wildlife images from Africa, and they're tasked with building a model which can identify animals in the image, whether this would be a classification or a regression problem, they're asked to explain why. Suppose the student says or answers, I think it's a classification task, but essentially what we wanted to also get from the student in this case is the correct type of explanation for that, to understand whether they grasp this concept of the relation between the types of the outputs here and the particular types of tasks. So ideally, what we would like to be able to do with the system is to say that bits of this answer is correct, but what is missing here is the reasoning. So this is the particular research question that we addressed in this work that is referenced from the slide. And in that case, the students will receive a more precise, more focused feedback, and hopefully on the basis of that, will be able to actually answer and elaborate on the answer that they provided in the first place. So this is the visualization of the feedback system that we implemented, and I'm going to walk you through this system bit by bit. So the first bit that we have here, and the very first step that we do, is we would like to identify what are the discourse units, the elementary discourse units within the answer, and how they relate to the elementary discourse units in the reference solutions. So because we have this set of reference solutions, even though they're diverse at the core, they use very similar structure. So there would be the answer, as in, for example, it's a classification model, and there would be the explanation reasoning for it. They may be phrased differently, but this is still the core that we would like to see in the answer from the students. We would like to be able to evaluate each of these bits for their correctness. Therefore, the first step is to be able to split the answer from the students into these bits. So if the student answered, I think it's classification, because we're choosing between continuous values. Bits of this answer are incorrect. So we'd like to identify which ones. So we'd like to explain to the students what exactly they need to fix. So ideally, we'd like to split it into, I think, it's classification, and because we're choosing between continuous values. So how do we do that? We train the segmentation model that is aimed at splitting the input sentence into this elementary unit. So we have training data that comes from the rhetorical structure theory discourse tree bank. And what we are doing here, we are modeling coding the bits of this, so the bits of the sentence token by token. And what the model aims to predict, as you can see in this example on the top, it aims to assign 1 to the words, to the tokens that start the elementary unit, and 0 to all the other tokens. So ideally, it would split the sentence here into, I think, as you can see within coding, its classification as the second chunk, or the second elementary discourse unit here, and the rest of it will be the third one. So this is the very first step, to identify such elementary discourse units in the correct solution in the reference answers that we have on the platform versus the student solutions. Why do we want to do that? On the basis of these EDUs, elementary discourse units, we would like to then be able to tell whether each of them is correct or not. And this we do by semantic similarity. So the idea here is that, suppose in the reference solutions that we have on the platform, separate classes are mentioned. So we don't see actually, say, discrete outputs. But if the student answers discrete outputs in the correct part of this answer, then we want to be able to identify that these answers are semantically similar. So this is the correct answer, even if it's not mentioned precisely word for word as what we have in the reference database. On the other hand, continuous outputs do not mean the same thing as, for example, separate classes. And therefore, they will be different from the answers that we have in our database. And even though we can't cover all of those potential answers, we would like to be able to identify that this is where the error is. Okay, so once we have identified these discourse units, and we are able to also judge about the correctness of each of them, the other key bits to this system is also to be able to identify whether the relation that holds between these different bits is the correct one. So specifically in this case, we are looking for an explanation. So I think will be the beginning of this. So the first EDU, the way it is related to the second bit of the answer, which is its classification, is defined by the relation called expansion. The third bit here is called contingency. We're using here the terminology from the Pan discourse tree bank, where they distinguish between these different types of coarse-grained relationships. So contingency stands for the cause. So in the reference solutions, in the correct answers, we are seeing that most of the answers that we have contain this core, like its classification, and then the contingency or the cause relation that links it to the explanation that is provided. So that's what we would be looking for in the solutions from the students. So in that case, what we would like to do is we would like to learn what are these different types of relations in the reference solutions versus in the solutions provided by the students. And in that case, we are building the representations for the neighboring units, then we are concatenating them as the input to the classifier, and then the discourse classifier, essentially its goal is to classify these adjacent units into the relations that hold between them. So as an output here, we would like to predict the first one is expansion, and the relation between the second and the third EDUs is contingency. So having split or segmented the reference solutions that we would be expecting from the students into these EDUs and having identified the relations, we are able to build a so-called exercise graph. So this is how it works. Based on the segmentations and on the semantic similarity between the different bits within the reference solutions, we are building the graph where each node represents the EDUs within the reference solutions or within the solutions from the students. The relations you see on the arrows that are connecting these different nodes. So for example, whether the solution contains its classification or a classification task or classification would be clustered together on the basis of the similarity of these ideas. Therefore, this is the core bits that we would see in lots of answers that we would be expecting to get from the students. And then the cause may be presented with in different ways. So it can be, for example, because it uses categories, so because the outputs are discrete and so on. But the idea here is that we are clustering these different ideas, different EDUs based on their similarity. There may be more ways to express this idea as well. So the clusters grow bigger with respect to how many different solutions would contain these ideas. Here you see the examples of how it was split into these EDUs. And also, similarly, the relations would be stronger for the those relations that actually we observe in many of the solutions in our database. So this is summarized here. Larger clusters correspond to the commonly occurring ideas. Smaller clusters, therefore, probably represent some noise. If, for example, we apply this similar technique to the solutions from the students, since we see that they do not correspond to any of the clusters, this will likely correspond to some noise or the error. And in terms of the relations, the edges signify what are the common relations that stand between these adjacent units. And therefore, the stronger the connection, the more often we see such a relation that links the adjacent units, the adjacent ideas. The higher the weights that we would assign to such a connection here. So once we have generated this, we then go to implement the classifier that would identify which of these relations holding between the adjacent units are valid ones, which ones are invalid. The idea behind that is that if we were only comparing to the clusters that we built on the basis of our exercises, we will not be able to or if we were only comparing to precisely the solutions that we have already in the database, we would not be able to cover all the different possibilities of how the same answers can be expressed by various students. We don't want to precisely learn that this idea should always be represented as it is a classification task because it uses categories, and that's it. We want to be able to identify that any of these expressions here can be combined with any of the explanations given or provided that the right type of relation links them. So to do that, what we can do is generate more data representing these positive classes by sampling from the exercise graph that we created based on the reference solutions. And when we do that, we use the distribution and the probability of how often we see these different connections. So we sample the correct or valid representations, valid answers in that way. And we can also generate incorrect solutions as well. To do that, this graph probably wouldn't provide us with enough examples here because there's just one link, but if there were other relations that were linking the main answer to the follow-up expansions and explanations, then we can also sample some of the incorrect ones by using the plausible type of relation but the incorrect follow-up solution, for example. So what we are doing next is we are training the classifier based on this data that is actually present there, as well as this artificially generated data of all the different types, the distribution of the valids versus invalids. Examples that we generate is about 50-50, and then we train the classifier that is able to recognize which of these different types of examples would then be correct or incorrect in terms of the relation that holds between the different adjacent units and the way they're expressed. So this is the bit where we're generating these candidates, and as the next step, we are using these samples, and the model tries to identify between those two adjacent units with the representations being concatenated. We're using the multi-layer perceptron here to classify the relations into the valid ones or invalid ones. So as the very final step, then given the student solution, what we can do is, first of all, apply these steps and build a relation graph that is based on the solution from the students. Then we can see how it corresponds to the graph that we have built for the correct solutions based on our database. And then we can provide the students with more precise feedback given their particular answer. So for instance, if in this case, the answer was, I think it's classification, and we already sort of defined that in the previous examples, we already defined that it is missing an explanation or reason. So what we would like to do here, we would say that this is correct, but the cause is missing. So this is the precise feedback that we would like to send to the students. In that case, what we do now, using the model that we trained, that evaluates and assigns the probability score to the best sort of candidates from these to the most valid relations in this graph. First of all, we generate the candidates that would be the most similar to the candidates that we have received from the students. So in this case, for example, the ways we can modify this, the student's answer contains this bit, but it can either start at the starting point, so it will be its classification, or it can be expanded further. So we start with I think, and then the nearest sort of solutions, the nearest most similar variants that we would have here. I think it's classification because it uses categories, or I think it's classification because outputs are discrete. So those would be the candidates that we will be able to extract from such a graph. The model that is trained to evaluate this with respect to how valid they are will then rank the most probable, the most high quality ones of the list there. And suppose we have this one that is ranked as the most successful, the most high quality one. So now by analyzing what exactly is the difference between this the solution from the students and the solution that we're looking for, we know that this is the relation that links the previous ideas with the idea that is not present in the student's answer. And therefore, we are able to define that the feedback to the students would be their answer is correct, but it is the particular bit of the answer which is the cause, the reasoning that is missing. So the feedback here would be try to provide the reason for your answer. In general, the 4 different types of errors that we observe includes the following. So sometimes the bit would be missing, just like in this example, the reason is not provided by the student. Sometimes there would be extraneous information, in which case the feedback would be your answer is along the right lines, but try to shorten it. Sometimes the relation would be correct, but it is the specific content that is related to this idea that is incorrect, in which case, let's say, try, for example, changing your reasoning in this answer. And finally, a very rare case where the relations would be completely incorrect. And in that case, the best feedback that we can send or provide students with is to say that they should try to rethink this question. Okay, so in terms of the what is called intrinsic evaluation, that is when we basically evaluate how each particular bit of the system performs. In terms of the metrics that are traditionally used to machine learning models, we observe that our segmentation model, our discourse classification model, and the classifier that classifies whether the transitions between the adjacent units are valid or not, they all perform either on a par with the state-of-the-art results for each of these models, or they are actually outperforming those. And therefore, this is a reliable system to use with the actual students on the platform. And this is one of the benefits of working with a system that has an implementation that can be used by real learners there. Just what we can do, we can also evaluate how it affects the actual learning on the platform. And here are the results. So what we do here, we tested this in actual students, and we observed whether they were able to answer the question correctly after they were provided with this feedback. We distinguish here between two scenarios. We measure whether within the, so when they were provided with a question in the first place, they answered incorrectly, and before their second attempt at the question, they were provided with these hints. And then we measure whether they answered the question correct or not. These are the results. Basically, this is the percentage of times that, given the different models, they were able to answer correctly. In this case, all attempts includes all attempts at the exercise. Therefore, it means that this model might have contributed to the sort of acquisition of knowledge by the student, but maybe there were other factors as well. So it's not as strong. So the different models that we're distinguishing between provides the students with minimal feedback. That's where they just learn that the answer is incorrect. With the what we call cluster-based feedback, we say, for example, try rewarding. So we highlight which bit of the answer is correct, but we do not specify that. For example, it's the reasoning that is wrong. We just say try rewarding your answer somehow, and this is essentially very, very close to minimal feedback, but actually still providing students with a bit more information. And finally, the full feedback model, as you can see here, is the most successful one and outperforms the other models by a large margin. So now, the very final bit, how do we know that these models really work and have an effect on the learning for the students? So what we did, as is typical to answer such questions, is we ran comparative studies. And in this particular case, we ran the studies using our platform, which is platform B here, and we compared this to another platform, which is a very popular massive online open course platform used by lots of students all over the world. So as you can see in this visualization, essentially both platforms present the learning material in terms of video lectures. What is the key difference between the two is that on the MOOC platform, what students are getting afterwards is just multiple choice questions, and there is no interaction and no further active learning involved in that, and so there's no personalization. In contrast, the model that I have presented today involves all of these different aspects. So we have formulated the hypothesis that the learning with Korbit will be more successful in terms of the learning outcomes, because it employs this personalized active and problem-based learning on the platform and provides the students with a variety of these different types of interactions. So then we ran the study with 48 participants that were recruited from the universities. They were undergraduate students and they were beginners, which was essential because we wanted to eliminate the fact of students starting from different starting points. Then we provided them in both groups. We split them between the two platforms, and they did a 3-hour course in linear regression, which is one of the introductory topics that they could do. The achievements were measured as follows. First, we provided them with the quiz before they did the course, which we call pre-quiz, and then with the quiz afterwards. The two quizzes were aligned across the two platforms, and the material was also adapted on our platform to one on the MOOC platform. And therefore, in the end, so both of these pre-quiz and post-quiz sets of questions involve 20 multiple choice questions, so they are very similar across the two platforms. The results are measured as follows. So first of all, we can just measure the learning gain as the difference between the score that the students show after the course minus the score that they got before they did this course. And we also can normalize with respect to the ideal achievement on the course, which is 100% in the post-quiz, therefore the post score of 100%. So this normalizes for the different sort of the differences, individual differences between the students, and helps us to put everyone on the same playing field. So what we see here is that the Korbit platform provided students with, or the achievements of the students showed much higher learning gains, and the difference here was statistically significant. So in both, when we measured this with respect to raw learning gains and the normalized learning gains. That was one finding, but the other one that we also we discovered here is that as part of this test, we provided students with a questionnaire which contains a number of different questions, including how would you evaluate yourself, how much you learned with this platform. And they were offered a scale from 0 to 5. Essentially, as you can see, everyone selected a score from 3 to 5, but the key difference here is that, first of all, as you can see, with the Korbit platform, there is this nice increase. So what this shows is the alignment between what students thought they learned, how much they learned, to the actual learning gains that we observed in their tests. And here you can see that the students within the category where they said that they learned a lot with the score 5 out of 5, with Korbit platform do show the highest learning gains. And as you can see, these learning gains are twice as high as with the MOOC platform. Moreover, there is sort of a minimal difference between the categories of 4 and 5 for the students on the MOOC platform at the same time. And the actual learning gains do not really support the idea that they have learned more than within this category that's self-assessed at 4. So what does it tell us? This actually shows that students, when they are working through the exercises in this active mode, they get a more accurate idea about what they know, and this translates in better metacognition. So I mentioned this illusion of learning before, and this essentially relates to this idea. So until we start doing things, it's hard to understand how much we know. Therefore, students on the MOOC platform, they quite often overestimate how much they have learned through this process. But one of the concepts that probably was a confounding concept there was that there might have been more differences between the two platforms than just the interaction and the personalization, because the two platforms are essentially very different. There may be some design issues that were also at play and so on. So what we decided to do in this follow-up study is to also split the Korbit platform itself into 2 different modes. So this mode in the middle is the one that doesn't provide any feedback. So it's maximally similar to the MOOC platform in the sense that it will ask questions, just like the multiple choice questions, and then it would just evaluate the answer in terms of whether it's correct or not, but it wouldn't provide any further feedback. The hypothesis here was very similar as well. So we hypothesized that now the full feedback Korbit model will result in higher learning outcomes compared to both of these other systems. And indeed, when we tested this with the extended group of participants, we also observed very similar results to what we had in the previous study. But what we also observed is that with the full feedback Korbit model, students also spend more time on the platform. So they actually are working through more exercises and so on, which shows that they have high engagement and motivation than with the platforms that do not provide for such interactive content. And we also see that the exercise completion rates are high with this interactive platform, full feedback platform as well. So in conclusion, what we can say and what we have learned through these studies is that such personalized and active learning on this platform have a huge impact on learning gains that we've seen through the results, but also on the engagement and motivation for the students. And last but not least, on metacognition, so therefore how much students actually realize, how much they've learned with this. And this also tells us that in the situations where, for example, the in-person teaching is not available, or, for example, we'd like to complement it, this can be used as a way to provide students with high-quality education at scale. So those are the conclusions, and now sort of the next steps in this research that I would like to work on. So in addition to what I have presented, where we have already used the analysis of the interactions and the dialogue on the platform, to bring these ideas together, one next step is to be able to split any type of teaching or learning material, any type of content, into the key concepts that I have already talked about, and have presented this relation graph, but this also is related to the idea of, for example, a knowledge graph or knowledge base that we can use to represent the material in any subject. And this is where the machine learning and natural language processing essentially key to represent the material in this way. So suppose we were able to split the material into these key concepts and learn the relations that hold between them. So you've seen these examples about linear regression and the different types of outputs that these models produce and so on. So for example, the relation here would be reduces outputs, and then it would be related to the right types of outputs. So this would be the ideal representation of knowledge that covers all of the knowledge in a particular subject. Now, through the dialogue, we would be able to then learn about the concepts that have been mastered by the students and they haven't. And also on the basis of this graph, we will be able to identify what is the right way to present these concepts, and what is the right order, what are the prerequisites for the different types of concepts. So this is called goal-oriented, task-oriented dialogue system that actually follows this internal representation, the internal graph, and it knows what would be the next most reasonable question to ask the students about. So for example, in this case, if we don't yet know whether the student sort of understands what outputs are related to particular types of models, it makes sense to ask about that. And then following this graph, there would be further relations that are more advanced, that's more complex. And as soon as we know that this has been mastered, what would be the next type of exercise, next type of question to ask the students about? The further challenges and research questions here includes how do we actually build this? Obviously, we are not going to build this manually. Is it possible to transfer this across widely different domains? So, for example, in the STEM subjects, we have explored this to a certain extent, but we haven't looked into how to represent or how to apply these ideas to other types of subjects, for example, in humanities. And finally, as I mentioned, the idea is not to actually replace the human teachers, but rather to complement teaching, to sort of save more time for the more quality sort of discussions and digging deeper into the most interesting and most challenging questions. So how can we integrate such systems, and how can we actually complement the teaching in the classroom with the systems that would be able to provide us with these backgrounds and actually identify what we as students do not understand, or what we as teachers should be addressing and talking about in the classroom. So this research is done in collaboration with multiple universities in the UK and in Canada at the moment. And at that point, I would like to thank you for your attention, and we'll be happy to answer questions.
Interactive, intelligent responses.
Yeah.
Oh, thank you very much. It's very informative, clear, and interesting. So I have a general question. When you talk about personalization, right? To me, there are two kinds of personalization. Mm-hmm. One way is to condition on the observed features of the students or users, right?
Yes.
You observe my height, weight, age, and so on, and then every time when you try to recommend something, you condition on such information. The other way is to make use of so-called counterfactual reasoning. So that means, oh, I would like to infer the information of the hidden features that I didn't measure, and then recommend something accordingly. So in the literature, is there any work making use of the counterfactual reasoning procedure for this kind of personalization?
That's a very interesting question. So I would say that this is related somewhat to recommendation systems, for instance, report systems, where we are identifying what would be the latent features that would lead us to actually recommend something. Yeah. We would not be necessarily able to explain what these latent features are. I am not aware of any such research, and that's a very interesting direction to follow. So I think in terms of recommendation systems themselves, it would be relatively easy to adapt, for example, recommendation of YouTube videos to the interest of the students. If I observe that you have been selecting certain topics on the platform, like you've learned about neural networks and some specific deep learning techniques, then it would be reasonable to suggest something related to that and so on. So we can do that, but I don't think anyone has actually explored how successful this is and what are the results of that. But of course, the very first type of personalization that you mentioned is precisely what we are doing, which I haven't covered in depth today, but essentially this is when we select the exercises related to the performance of the students. So essentially what we are trying to learn is a proxy for how strong or weak perhaps the student is in certain subjects, have they succeeded in answering the previous questions and so on. So what would be the most reasonable interaction at this point? So this is more the direct one.
Thank you. Because to me, that's really essential. In classroom, even if our students look the same way, right? Still from some kind of difference in some kind of response, we can infer the information on hidden things, right? And then we can do something accordingly. So, okay,
absolutely. But can we do this on scale, for example? Can we do this at scale, like for multiple students and addressing this?
Easily derive some kind of standard procedure to achieve that. So that's why I think maybe in the future that will be something.
Yes, absolutely.
We can benefit from. Thank you.
Yes, I agree.
Okay, so thank you very much. For the evaluation, we had the MOOC and the no feedback and full feedback. You asked the student to do each one of these, right? So
no, actually they were split between the two, so they were non-overlapping. So those who did MOOC, the MOOC course, they didn't do the Korbit course and vice versa.
Right, because I was going to ask if they done that, the order may have.
Yes, yes, of course. But the courses were sort of very similar to each other, so that wouldn't make sense to make them go through both. But that's an interesting idea, which I have also thought about. So of course, then if they are doing both, then the order matters because they must have acquired some from the previous course as well. So then we can't separate what they have learned before with what they are learning with the course now. So in this study, they were split in the non-overlapping way between the two.
Thanks a lot for the talk. I have a question regarding the segmentation model. So you're using the segmentation model to segment the answer from the explanation, right?
Yes.
So then you can compute the semantic similarity between the answer and the reason. So what I want to propose is maybe trying to tokenize the sentence and without splitting anything, without passing it through the segmentation model, and then computing the semantic similarity of every set or combination of tokens with the answer in the database and the explanation. And if it's closer to the answer, then it is actually the answer. So you use the semantic similarity of the tokens for the Q as if it was the answer or the explanation. So for the example of the answer, yes, it's a classification problem. If you compute the cosine similarity, for example, between that and what's the answer in the database of that and the explanation, it will be closer to the answer. So that would be the cue that this is actually the answer. So the same thing goes for the other ones.
Yes, so what we do with the segmentation is we are essentially trying to build on top of the tokens. So some of these tokens, they are merged together into one super token, so to say. So I can see that your proposal, it will work for the examples where there is some close similarity indeed, so just something missing a bit. So these examples, it would probably apply to, but if we were observing more diversity in them, it would be essential to learn which segments correspond to which correct or incorrect segments. So that's why it will become challenging, the only using the tokens themselves. So that's why we need to merge this to actually make sort of sense of the high level units, but also learn the relations between these units. So for example, if we were only doing this on the basis of the tokens, we won't be able to necessarily say which tokens, without this further segmentation, which tokens relate to the explanation, to the reasoning, and which ones to the core answer, right? So that's one part of it as well. So the segments are further fed into the identification of the relations that we use for the feedback. Thank you.
We have a question. First, you compared the state of the art with your approach. What type of state of the art are they based on?
Yes, so I didn't mention the specific references here, so they would be in the original paper. I just thought it's a bit too much, perhaps, but they would.
In terms of F1 measures, I mean, does that matter in the design of your system?
Yes, so these are the metrics that relate to, it has the downstream effect on the learning, but essentially at the point when we are evaluating the components of the system themselves, what we want to know is that, for example, it is successful in segmenting the inputs into these chunks. So what this tells us is that essentially it can segment this with very very good results. And essentially, when we are comparing to the state-of-the-art models, so other types of deep neural networks that are applied to a similar task, we are performing in a similar way or even better. So the lower the results here, the less reliable the segmentation itself would be. So if the segmentation is not reliable, then as the sort of downstream results, the feedback would also be not as good, because we won't be able to identify precisely the bits of this answers. That's why it matters. So it has this further effects for the results and the impact on the learning. At that point, it's just about the model itself.
And we design the system to have students and the children part. Can we have also instructors asking questions in this approach? For instance, to check whether the students is recognizing shallow information or the best possible approach?
Yes, that's a good question that relates to how we can use this system in real time. Of course, it has a bit of this overheads where we have to calculate all those things. So we haven't tested this with real-time questions, but I think it would be very good if we could do that. And it falls within this final bits of the research that I described, where I would like to see how it actually aligns and how it can help lecturers and teachers. So one way I can see that is, for example, you give a homework, and then after that you see as the lecturer or the teacher the results of this, how students actually understand the subject, and what are these knowledge gaps that you need to address in the classroom. But of course that relates to the idea that it's all sort of not real time. So we can provide the feedback in real time, but evaluating new questions, that would require a bit more research. So I'm sure it can have enough effort.
We're unfortunately going to have to leave it there. We're out of time. But
thank you very much.
And you again.